Okay, we're going to go through Review Exam 3 solutions. So here we have a repeating decimal and we want to write it as a fraction. So first write it as a geometric series. Now in order to use this geometric series formula, which converges for absolute value of r less than 1, we factor out 15 over 100. So this starts at 1. So this is equal to 15 over 100 times 1 over 1 minus r. In this case, r is 1 over 100. And you just work this out and we get 5 over 33. And number 2, we also have a geometric series. Okay, so let's write it out. Notice that it starts at n equal 10. So again, factor out the first term so that we have it starting at 1. All right, so that we can use our 1 over 1 minus r formula and just figure this out, and this is what we get. All right, whenever we are asked to find the sum of a series, usually, almost always, it's either a geometric series like we have here, or this is called the telescoping series, where we factor the denominator. This is another type of series where we can sometimes find the sum. If we factor the denominator and break it up as partial fractions like we're doing over here, okay, so factor the denominator n times n plus 2 and write that this is equal to a over n plus 2 plus b over n. Now we've multiplied both sides by n over n plus 2. So here the n plus 2 cancels and we have an. And here the n's will cancel and we have bn plus 2. Now substitute into this, first n equals 0 so that this drops out. And we have minus 2 is equal to 2b, so b is minus 1. And then substitute in n equal minus 2. All right, and then that will drop out. So we have minus 2 equal, this drops out, so we have minus 2 is equal to n equal minus 2, sorry, n equal minus 2, this drops out. Oh, sorry, I'm down here. Okay, I think I wanted to write, let me just put, all right, here we're substituting in the n equals 0, and here we're substituting in the n equal minus 2. So when we substitute in n equals 0 here, the a drops out, and we have minus 2 equal 2b. So b is minus 1. When we substitute in n equal minus 2, this drops out. Minus 2 equal minus 2a, we have a equal 1. All right, so in other words, this is 1, and this is minus 1. Okay, so substitute that in here, 1 minus 1 for b. Okay, and let's write out the first few terms. We're starting at n equal 1. So we start at 1 over 3. 1 over 3 minus 1 over 1. Then 1 over 4, etc. And now just see what cancels. Sometimes some things in the front are left. All right, so this 1/3 cancels with this minus 1/3. Or looking at it the other way, minus 1/3 cancels with 2 terms ahead of it, with the plus 1/3. So this, and this minus 1/4 cancels with 2 terms ahead with the plus 1/4. So everything, all these second terms cancel with 2 parentheses ahead. Now this does not have, this is the first term that doesn't have 2 parentheses ahead. Okay, we only have 1 set of parentheses ahead. So minus 1/2 has nothing to cancel with, and minus 1 has nothing to cancel. So we're left with minus 1 times minus 1/2. Everything else cancels. So this sums to minus 3 over 2. All right, in number 4, we're just asked if we have a converging series or not, converge or diverge. All right, so over here, we are going to look at the term n squared over square root n cubed plus 1, and let's first of all see if this goes to 0. If it doesn't go to 0, then it definitely does not converge. We divide top and bottom by n squared. All right, so we have 1 here. Now underneath the square root, n squared becomes n to the 4th. All right, so here we have n cubed divided by n to the 4th. That's the 1 over n. Here we have 1 over n to the 4th. So when n goes to infinity, both of these are going to 0. So this fraction goes to 1 over 0, so that diverges. In other words, a to the n definitely it actually goes to infinity. Okay, or a to the n does not go to 0. So that means diverges. Okay, in B we have an alternating series, and we have alternating series because it's minus 1 to the n. So for alternating series to show convergence, we need to show two things. We have to show here that a to the n plus 1 is less than or equal to a to the n. In other words, that the absolute value of the terms go to 0. And we have to show that a to the n goes to 0. Sorry, not the absolute. Here we have to show that the absolute value of the terms goes to 0. That's here. And here we have to show that we have decreasing terms in absolute value. All right, so it's not hard to show. First of all, this part is easy. These do go to 0. Obviously, the denominator is going to infinity. That limit is 0. So that's easy to show. Here, the way we usually show that the terms are decreasing, or that one term is less than or equal to the term before it, is we replace n with x, and we look at that function. All right, again, we're looking at the absolute value replaced with x. Take the derivative, and because of this negative here, we have something that's always negative, so that means our function decreases. F of x decreases. All right, so that shows this. Continuing with number 4, we want to see if this series converges. So we're going to do a ratio test. So we look at the n plus first term divided by the nth term in absolute value. All right, so it's the same thing. This is the n plus first term, and we're multiplying by the reciprocal of the nth term. So that's the same thing, just reduce. And here we have n plus 1 over n, and reduce this way, and we have 1 over 2. And then take the limit as n goes to infinity. Well, this piece over here, that goes to 1, so we're left with 1/2. And 1/2 is less than 1. So by the ratio test, this converges. Okay. The ratio test actually shows absolute convergence. But anyway, this is positive, but that's one thing we get from the ratio test. Okay, let's go to the next one. All right, in D, we have 1 over n to the 3/2. Okay, let me just look at that review sheet. Is that what I have there in D? Yeah, and that just converges by the p-test. P is 3/2, which is greater than 1. Or you can do an integral test, and if you integrate this from 1 to infinity, you'll see it converges. Okay, for E, we're going to do an integral test. Okay, because we have a nice setup for an integral. We have an inner function ln x, and the derivative of ln x is 1 over x, so we have the derivative of the inside sitting on the outside. So this is the result of a chain rule differentiation. So we can figure this out without doing a u substitution. Just do the power rule on ln x to the minus 2, add 1, and divide by minus 1. Okay, so you can just check this by taking the derivative to see this is the right antiderivative. Just bring down the minus 1 and subtract 1, and then we would get ln x to the minus 2. And then chain rule, we do the derivative of the inside, and the 1 over x would pop out. Okay, put in the limits, 2 to infinity. Okay, so when we substitute in infinity, we'd rather put an r here instead of infinity and look at the limit. R goes to infinity. All right, so that would be our first term. That goes to 0 because ln r is in the denominator and ln r goes to infinity. So this whole thing goes to 0. And then we're subtracting what we get when we substitute in 2. Because of the minus, we have plus 1 over ln 2. All right, so that's finite. So that means our sum converges. Because by the integral test, these are going to either both converge or both diverge. Okay. And now let's look at F. Okay, so here we're going to do a limit comparison test. Now to see what to compare with, we just look at the top and the denominator, and look at the denominator without the 2, because when n is large, this 2 is not going to be very significant. So to compare it with something simpler, we compare it with the sum n over square root n to the 4th, which is n over n squared, or 1 over n. Okay, now comparing to 1 over n, we're doing the limit comparison test. Limit comparison test is we take, if we have two series, we see if they're similar by comparing, let's say, bn over an. You can do an over bn or bn over an. And we want to see if it goes to L, where L is finite and L has to be greater than 0. All right, so we took one series, the 1 over n series, and put it on top of this one. Okay, so we're going to compare with sum 1 over n. And, all right, let's take the reciprocal of the denominator. We have that. All right. Then we're going to divide by n squared underneath. So that's the same as dividing by n to the 4th underneath. So we get 1 plus this. All right, so we end up with square root 1, or 1. Now 1 fits this criteria for L. It's bigger than 0, and we don't get, it's not infinity. So that means it does whatever this series does, that this and this converge or diverge together. Well, this one diverges by the p-test. So we did the limit comparison test with something that diverges. That means this one must diverge as well. Okay, so that's what we have. We have divergence over there. All right, so let's look at G. Okay, let me just see, is this the last one in here? No, we have a few more. Okay, so let's look at G. Now what we're doing here is, this time we're going to be able to do a direct comparison test. All right, so let's see what that is. So again, we're going to just ignore the 1, okay, because when n is large, this 1 is very small, relatively. So we just look at n over square root n to the 5th. This is n divided by n to the 5 halves. That's n to the 5 over 2. And just simplify 5 over 2, subtract 2 over 2, we get 1 over n to the 3 halves. This converges by p-test. All right, now notice that this term in our series is smaller than this one, because this one has the plus 1 in the denominator, making it smaller. All right, so since this one converges, this series converges, this one's even smaller, so by the limit comparison test, this one also converges. Okay, let's look at here H, for H. All right, so here we have an alternating series because of that minus 1 to the n. So we have to show two things. First of all, we have to show that a to the n goes to 0, which it does, all right, because ln n is going to infinity, so that does go to 0. Then we also have to show that a to the n plus 1 less than or equal to a to the n. All right, so we do this by looking at the function, the corresponding function, 1 over ln x, and seeing if the derivative is negative. When we take the derivative, we get this, and for x greater than or equal to 2, this is negative. All right, so that means that f of x decreases, and so this one does as well. Okay, this does as well. So that means showing those two things means we have convergence. We actually have, in this case, conditional convergence, since the absolute value does not converge. That we can see easily. This diverges. So that's called conditional convergence as opposed to absolute convergence. All right, let's look at I, for I. So we have n to the n over n factorial. All right, now n to the n is bigger than n factorial. Okay, so this is definitely going to diverge. But if you do the ratio test, let's see what happens. So the ratio test, you have the n plus first term. Okay, so we have, this is the n plus first term. Divided by the nth term, take the reciprocal, instead, okay, which is equivalent to dividing. Now let's simplify this. So when we divide this way, we're left with n plus 1. And divide this way, and we're left with n plus 1 over n to the n. Let me change this a little bit, 1 second. Okay, I just made a little correction, so let's reduce this. Okay, so here's what we have. Okay, reducing this way. Now let me split this. Okay, reducing this way, we have that this is equal to, we have an n plus 1 in the denominator. All right, and then let me just break off one of the n plus 1s from here. And then here we have n plus 1. Then we're left with n plus 1 to the n here, and then we have n to the n. Okay. All right, so what we end up with, this is kind of interesting, is we end up with n plus 1 over n to the n, which is equal to 1 plus 1 over n to the n. And then if we take the limit as n goes to infinity, this is actually the definition of e. We get e, which is greater than 1. All right, so that implies by the ratio test that this diverges. Okay, however, you can just look at this over this and see that it's not that the limit as n goes to infinity of each term is not 0. Because if we look at the various terms, each factor is greater than or equal to 1. Okay, so that can't go to 0. Each one is greater than or equal to 1. So that can't go to 0. All right. But anyway, the ratio test just does show that it diverges. All right, let's go to the next one. Here we want to do the ratio test. 2 to the 4n over 2n plus 1. So put an n plus 2 here, and we get put n plus 1 over here, and we get 4n plus 4. And here put an n plus 1, and this is what we have. Okay, and then multiply by the reciprocal of the nth term. Just multiply by that reciprocal. Now start reducing. So reduce this way, and that's where you get 2 to the 4th. All right, now this way, we're going to have, this is 2n plus 3 over here. 2n plus 3 times 2n plus 2, and the rest cancels with that. As n goes to infinity, this is a constant. This gets bigger and bigger, so this goes to 0, 0 less than 1. So by the ratio test, we have that this converges. All right, let's look at the next one. Again, ratio test. Okay, so we'll do the n plus first term. So we have n plus 1. Here we have n plus 1 squared. Okay, and then divide by the reciprocal of the nth term. So here's the reciprocal. Do some reducing right here, and we just get 3 over 2. And here put the n on top of the n plus 1 squared. Okay, this goes to 1, this piece. That piece goes to 1. So we get 3 over 2, which is greater than 1. That means that this diverges by the ratio test. For the ratio test, we need to get something less than 1. So that diverges. Okay, so let's look at number 5. So we want a degree 2, just degree 2, Taylor polynomial of this about c equal pi. So we're going to take the derivative twice, okay, and first starting with the function, substitute in pi. Okay, so here we have pi squared and cosine pi. Now cosine pi is minus 1, so that's minus pi squared. All right, and now first derivative, we do a product rule. So we have the first times the derivative of the second. Derivative of cosine is minus sine. So we have that plus derivative of x squared, 2x times cosine x. Now put in your pi. Okay, this is 0, sine pi is 0. So here we have 2 pi times minus 1, minus 2 pi. Okay, now the second derivative, we're going to do the product rule twice. So the first time, we have the first times the derivative of the second. Derivative of sine is cosine. Plus the derivative of minus x squared, that's minus 2x, times the second. And now this term. Okay, the first 2x times the derivative of cosine, which is minus sine x, plus the derivative of 2x times the second. Okay, now we're just substituting in pi. So here we have a cosine, again, of pi is minus 1. So we have minus pi squared times the minus 1, so that's pi squared. This is 0, this is 0. And now substitute in pi here, we have minus 1, so we have minus 2. All right, second polynomial, second Taylor polynomial, start with the constant term. All right, then we have this value, minus 2 pi, I can write over 1 maybe, over x minus pi to the 1. Okay, now the second derivative value here, over x minus pi squared divided by 2, or you can think of it as 2 factorial. So that's the second Taylor polynomial. Okay, number 6, we need the interval of convergence for a lot of different series. So let's start with A, interval of convergence. We always do the ratio test for this. So the ratio test gives us x over 5, which is, and we want to know when is this less than 1. This is less than 1 when the absolute value of x is less than 5. So that's our radius of convergence. But what about the endpoints? What about 5 and minus 5? Well, when we have 5, minus 1 to the n diverges, and minus 5, that also diverges. Okay. Just a minute, 1 second here. Okay, here we have minus 1 to the n. Now, here when x is equal to minus 5, we have minus 1 to the n. And if we substitute in the minus 5 over here, we're going to get minus 1 to the n again, another minus 1 to the n. So this is sum 1 to infinity, minus 1 to the 2n. So this time we're just adding up a bunch of 1s. Definitely diverges. Okay, this one we had minus 1 plus 1, and then minus 1 plus 1. It still diverges. So this is the interval of convergence. Okay, we're continuing with number 6, and we want to see 6b now, interval of convergence. So again, we do the ratio test. All right, so we have the n plus first term. I got rid of the minus 1 to the n because we're taking absolute value for the ratio test. So we have n plus 1 here, n plus 1, 5 to the n plus 1, and then the reciprocal of this. Okay, and now start reducing, and here we get just x to the x minus 1 to the 1. And here we have n divided by n plus 1, we put that here, and 1 over 5 when we reduce the 5 to the n over 5n plus 1, 1 over 5 here. Okay. This is going to 1. So now when we take the limit, we get x minus 1 over 5. We want that to be less than 1 for the ratio test to say that our series converges. So we need absolute value of x minus 1 less than 5, or just open up the absolute values and then do plus 1 plus 1. So we have x between 6 and minus 4. And now we have to check the endpoints. So let's see what happens at minus 4. Okay, when you substitute in minus 4 minus 1, you get minus 5. So minus 5 to the n over 5 to the n, that's minus 1. So we have minus 1 to the n, and here we also have another minus 1 to the n. Similar to what we had in that previous problem. This is another minus 1 to the n. N plus n is 2n, so we have minus 1 to the 2n over n. Now, minus 1 to the 2n, that's always 1. That's just 1. This is an even exponent. So we have sum 1 over n that we know diverges by the p-test. So at x equal minus 4, do not include that in the interval of convergence. Now, what about x equals 6? Okay, so 6 minus 1 is 1. So we get this series. This converges. This is an alternating series. The terms are going to 0, and they are decreasing. All right, so we do include the 6. You see the square bracket here, and we don't include the 4. We have a round bracket here. Okay, so this, or you could write it like this, greater than -4 and less than or equal to 6. All right, so let's just continue down. We're looking at C. All right. Ratio test, bump this up to n plus 2, n plus 2, and make this n plus 2, and then reciprocal. Okay, reciprocal of this, n plus 1, 3, n plus 1 on top, and that in the denominator. Start reducing, reduce this way, and we just get x minus 1. Okay, put this on top of this. This is going to go to 1. And then here we have a 3 in the denominator when we reduce. Goes to this. We want this to be less than 1. Okay, that means we want x minus 1 to be between 3 and minus 3. Add 1. We get a 4 here and a minus 2 here. Okay, and then again we have to check the endpoints. So let's check x equal minus 2. All right, minus 2. So we have minus 2 here. Minus 2 minus 1, that would be minus 3. And here we have a 3, so that gives us minus 1 to the n plus 1. That's that minus 3 over the 3 to the n plus 1 gives us minus 1 to the n plus 1. So that one's going to converge, like in the previous example. And when n equals 4, then we get 4 minus 1, we get 1 over n plus 1, and that one diverges. So this is just like, you can compare this, it's really basically the same as sum 1 over n. They both diverge. Okay, they both diverge. So, so there we have the interval of convergence. Include the minus 2, don't include the 4. Okay, D, let's just look at D quickly. Okay, we have this ratio test, and bump this up. If we substitute n plus 1, we get 2n plus 2. And here we get n plus 1 factorial. Reciprocal. Reduce, and we have x squared on top. N plus 1 on the bottom, which for every fixed x, this goes to 0. So that means this always goes to 0 for all x. So that means the interval of convergence is minus infinity, infinity. And we have something similar in E, or the same type of thing happening. All right, ratio test, n plus 1, xn plus 1, 2n plus 2. Reciprocal, 2n factorial, n factorial, x to the n. Now start reducing. Okay, here we get just n plus 1. That's that on top. This, we get x. And then here we have two terms, 2n plus 2, 2n plus 1. Okay, and as this goes to infinity, as n goes to infinity, this is going to 0. This is like an n, the largest term on top is n over 4n squared. So it goes, if you just take the highest power on top, highest power on bottom, you have n over 4n squared, which is equal to 1 over 4n. And now for a fixed x, okay, this goes to 0. X is fixed, only n's going to infinity. So again, the convergence is minus infinity, infinity, the entire number line. Here we want the power series of 1 over 1 minus x squared. That's simply a geometric series with x squared substituted in instead of r. And so this is sum n equals 0 to infinity x to the 2n. And if we want to know the interval of convergence for this, we again do the ratio test, and we get x squared. Now when is x squared less than 1? That is, when is x squared minus 1 less than 0? So we can factor this and do a plus minus analysis. The two zeros are minus 1 and 1, and it's negative in the middle. So the convergence is between minus 1 and 1, and it diverges at plus or minus 1. That's easy to see. First of all, the denominator is 0 at plus or minus 1. So definitely diverges at plus or minus 1. Okay, number 8, we want the power series of this centered at c equals 0. Now we don't have to use the Taylor series formula. We can use 1 over 1 minus r. All right. This is 3. We want that to be equal to 1. So start by dividing top and bottom by 3. And then we want the 1 here on the left. So flip it around to 1 minus minus 5x over 3. So we have put the 1/3 in front, and that's our r right there. So just put that in where r is. Okay. So we get a geometric series, and we know it converges if the absolute value of r is less than 1. So write that. That's our r. And that means that if you just multiply top and bottom by 3 over 5, the absolute value of x has to be less than 3 over 5. Okay. So this is the interval of convergence. Okay, we know that r has to be less than 1, so we, just by the geometric series formula, we know that if r is 1 or minus 1, it's going to, sorry, if this is 1 or minus 1, it's going to diverge. So definitely less than 3 over 5. And in any case, you could see if x is equal to minus 3 over 5, you get 0 in the denominator. Okay. If it's equal to plus 3 over 5, you get this series, 1 minus 1, 1 minus 1, which diverges. Okay, so do not include the endpoints. All right, now here in this one, we wanted to first find the power series of 1 over 1 plus x squared. So again, use the geometric series formula. It's 1 minus, and then parentheses minus x squared, and then just put that in. And we get minus 1 to the n, x to the 2n. All of these exponents are positive. Now arctan x is the integral of 1 over 1 plus x squared. All right, so that's what we have here. Just integrate, so we want to just integrate this by the power rule, 2n plus 1 over 2n plus 1. Just do the power rule. But the plus c pops out, and we have to resolve what c is equal to. So since we know one value of arctan 0 is equal to 0, if we substitute in 0 on both sides, we do get c equals 0. All right, for 10, we want the first 4 terms of the Taylor series. So here we're just going to use the Taylor series formula. Make this little table, look at f of x, and we want at c equals 0, or about c equals 0. Okay, substitute in 0, we get 1. Okay, take the derivative, substitute in 0, we get a half here. Derivative again, bring down the 1/2, we get I think we should have a minus over here. Let me just check this. Okay, I just have to put a minus in here. Take the derivative, and the minus 1/2 comes down, so this should be negative. And then that should be negative over there when we substitute in 0. And then bring down the minus 3/2, and so now this is positive. And this should be positive here. Okay, so here we have the first term is 1. The second term is 1/2 to the x. Okay, and then the third term we have minus. Okay, this should be negative. 1 over 2 squared, and here we have positive. 3 over 2 cubed. Here we have x squared over 2, and here we have x cubed over 3 factorial. So that's the first 4 terms, 1, 2, 3, 4, of the Taylor polynomial. Okay, here in number 11, we're looking at the first 4 terms of the Taylor series for this function. And we're just going through the basic calculation for the Taylor series polynomial. Okay, so here's f of x, here's f prime. We sort of have a pattern over here, f prime minus sine squared plus cos squared. If we substitute in 0, since sine 0 is 0, we get 0. All right, now at the first derivative, remember sine 0 is 0, so here we get cos squared. Cosine of 0 is 1, so we get 1. Okay, the second derivative, take the derivative of this, use a product rule, and we get this. Substitute, we get 0, and just keep on going like this. Okay, and I won't go through the whole calculation, but this is the basic Taylor series polynomial. All right, so this is 1, 2, 3, 4, the four non-zero terms. So let me just remind you, the polynomial looks like this. So this is coming from f0, then the first derivative. You can think of that as over 1 factorial, and then the second derivative, 2 factorial x squared, and it just goes on like that. So we did seven of these terms. Okay, here we want the power series for e to the minus x squared. So here's the power series of e to the x. Like I said, this you should know. And then just substitute in minus x squared. So this starts to alternate and all the coefficients are even. All right, and here's the general form. All right, here we want to find, I changed this. This was 5 originally. I changed it to 3 because it started to get very lengthy. So we want to find the first 3 non-zero terms of power series for this times this. Now, I'm not assuming that you memorize this power series here. I gave it to you, okay? And we're just going to start multiplying, and we want to get the first 3 non-zero terms. So do it systematically. Start with 1 to get the lowest power term. So that would be 1 times x. So we don't have a constant term, but our x to the 1 term is x. I'm going to put it within parentheses the x terms, the x squared terms. Okay, now for the x squared terms. Okay, so we'll start with 1, and we have 1 times minus x squared over 2. Then move to x, and we have x times x. So this is how we do this systematically. Move to x squared over 2, and we don't get anything. So that's the x squared terms, and now we're going to the x cubed terms. Okay, so start with 1, and we have 1 times x cubed over 3. Then go to x, and we multiply by this, and we have minus x cubed over 2. Then go to x squared, and that multiplies with x, and we have plus x cubed over 2. And that's all we need to do for this. Okay, notice these two cancel, and then you would just combine the like terms. Okay, in number 14, we're asked to estimate e to the minus 1, and we want our estimate to be, we want an error that's less than 0.001. All right, so the general term is 1 over n factorial. So 1 over n factorial is the general term in absolute value. Okay, so we keep trying 1 over n factorial and see if we get something less than 0.001. All right, we substituted in minus 1 for x here. Okay, so 1 over 6 factorial is this, so we have to get up to 1 over 7 factorial. That's 1 over 7 factorial, so that's less than 0.001. So we're going to use the first 6 terms. Again, the only reason why we have this error is because this is an alternating series. So the first term not used is our error term. That only happens when we have an alternating series. Okay, so what is e to the minus 1? Just use the first 6 terms, well, that is our estimate, and this is what we get for our estimate.